Right now, there are robots driving across the surface of Mars. We have flown a spacecraft past Pluto and taken close-up photographs of it. We have even dropped a probe down into the clouds of Saturn. There is one place much closer than any of those that we have almost never visited. It is the open space directly above the Sun and directly below it. Picture the solar system the way it is always drawn, flat, with the planets circling the Sun like marbles rolling on a tabletop. Everything we send into space tends to stay on that tabletop. Going straight up off the table into the empty space overhead turns out to be harder than crossing all the way to the farthest planet. So tonight, we go looking in the one direction we almost always skip. What is waiting up there? Tonight we are going to look in that one direction almost nothing ever travels, straight up out of the flat world we live in. Before we climb, it is worth holding still over a simpler question that has to come first. Why is there a flat world to climb out of at all? Picture that tabletop again, the Sun in the middle, the planets circling it on one level surface like marbles set rolling around a table. Nothing is actually holding them at that level. There is no real tabletop, no floor under the planets, no shelf, no pane of invisible glass keeping them in line. And there they all are anyway. 8 planets, dozens of moons, millions of asteroids, and nearly every comet, circling the Sun inside almost the same thin, flat layer of space. Something pressed them into that shape long ago. The question is what? To find the answer, you have to travel back about 4.5 billion years, long before the Earth existed, before there was a single rock or a drop of water anywhere near here. All of this, the Sun, the planets, the ground you are lying on tonight, was once a single giant cloud of gas and dust drifting in the dark. It was enormous, far wider than the entire solar system is now, cold, thin, and shapeless, floating between the stars. And that cloud was doing one quiet thing that would decide everything. It was turning. So slowly you could never have watched it move, but turning, all the same. Why turning at all? Because it formed from older material that was already drifting and circling, and out in space, once anything carries even the faintest spin, it holds on to it. Then gravity went to work. Every part of the cloud pulled on every other part, and the whole thing began to fall inward, shrinking toward its own center. And as it shrank, that slow turning sped up. You already know this feeling in your own body, even if you have never named it. A spinning skater pulls her arms in tight and suddenly whirls faster. A child on a spinning chair tucks their legs up and speeds right up. Drawing inward makes spinning faster, every single time. So the cloud, collapsing in on itself, turned quicker and quicker, and the faster it turned, the more that spinning took command of what happened next. Watch what spinning does to something soft. Picture a lump of wet clay sitting on a potter's wheel. While the wheel is still, the clay is just a round blob. Now set the wheel spinning and press down on the clay with your hands. The blob flattens and spreads until it becomes a wide, smooth, level plate. Watch why it does that. Pressing straight down from the top meets nothing that pushes back, so the clay sinks easily in that direction. Out to the sides, the spinning flings the clay outward and holds it there, spread flat and wide across the wheel. The cloud out in space did the very same thing, only there were no hands. Gravity did the pressing, and the cloud's own spin did the spreading. Straight up and straight down, Along the line, the cloud turned around. Nothing held the gas up, so it simply fell inward and collapsed toward the middle. Out to the sides, the spinning pushed everything outward and kept it from falling in. To collapse sideways, the cloud would have had to give away its spin first, and there was no way for it to do that. So the top and the bottom caved in. The sides held firm. A round cloud slowly crushed itself into a flat turning sheet, a disk. That is the part worth holding on to. The flatness of our solar system was never planned. Nobody designed it. It is simply the shape a spinning cloud settles into, every time, given enough years. Leave almost anything turning under its own gravity, and sooner or later it goes flat. It is hard to picture just how flat the result really is. The planets are spread across billions of miles from one edge to the other, and yet they all stay inside a thin slice of that space from top to bottom. Shrink the whole solar system down to the size of a dinner plate, and the planets would all ride inside a layer thinner than a sheet of paper laid across it. That is how completely the solar system commits to being flat. Now the cloud had its shape. Next it grew a center. Most of the gas slid down into the middle and piled up into one dense, hot ball. That ball squeezed itself tighter and tighter until it caught fire as a star. That star is our sun, and all around it, spread thin across the flat disk, the leftovers slowly drew together. Specks of dust drifted into specks of dust and stuck. The grains grew into pebbles. Pebbles smashed and clumped into boulders. Boulders swept up more and more as they circled, growing into whole worlds. Those growing worlds became the planets. And because every one of them took shape inside that same flat disk, they were all born already moving the same way, in the same plane, like runners who all started out on one shared circular track. So where is that disk today? It is gone. The young sun grew bright and fierce and blew the leftover gas and dust out into space long ago. So why are the planets still flat if the thing that flattened them has vanished? Because by the time it vanished, its work was already done. The planets had taken on its shape and its motion, and nothing was left to pull them out of line. They kept circling in the plane they were born into, the way a river keeps following the valley that shaped it long after the rain that carved it has dried up. And they have stayed in that plane ever since, lap after lap, for billions of years. Picture a stray rock circling the sun on a steep slant, cutting up through the crowded disk and back down through it again on every loop. Crossing all that traffic, it would eventually crash into something, or swing too near a giant planet and get flung away for good. The pieces that matched the flat plane survived. The steeply tilted ones were knocked out, one by one. So the flatness we see now is partly the shape the planets were born with, and partly what is left after billions of years of quiet clearing. And this is not only our story. The same thing happens anywhere the universe puts spinning and gravity together in one place. The rings of Saturn are a flat disk of countless chunks of ice, made in this exact way. Our whole galaxy, the Milky Way, is a flat disk of countless stars, made the same way, just unthinkably larger. Even the gas pouring into a black hole flattens into a spinning disk as it falls in. Flat is not the rare, strange outcome. Flat is the ordinary one. A solar system shaped like a ball, with planets looping over the sun and under it in every direction, would be the truly bizarre thing to find. And all of this is still happening to you, right now, tonight. The floor beneath you is not holding still. The whole Earth is sweeping sideways around the sun, carrying your bed, your room, and your body along with it, riding the very same flat plane that clouds settled into 4.5 billion years ago. You never feel it, because everything around you moves together, perfectly smoothly, exactly as it has every single day of your life. Every second you have ever lived, you have been gliding sideways through that plane, and not once, not for a single moment, have you ever moved straight up out of it. So we are back where we began, with one thing still unanswered. We know the plane is real now, and we know why almost everything stays trapped inside it. The plane has a top and a bottom, though, and a direction that points straight out of it, up on one side, down on the other. The one direction the planets never take. If the whole solar system agreed on flat all those billions of years ago, then who ever decided which way is up? Right now, lying where you are, you know exactly which way is up. Up is over your head. Down is the floor beneath you, the ground under the building, the center of the earth far below all of it. You have never once been confused about it. Up and down feel like the most basic facts there are. They are not. They are a gift from the earth, and the moment you leave it, the gift quietly disappears. The reason you feel an up and a down at all is gravity. The earth is enormous, and it pulls everything toward its center. That steady pull is the thing you call down. Up is just the opposite of wherever the pull is dragging you. So down is not really a direction out in space. It is only the direction toward the nearest big lump of matter. On Earth, that lump sits under your feet in the same direction your whole life. So down always feels like one fixed, permanent thing. Picture two people wide awake at the same moment. One standing in Canada, one standing in Australia. Each of them completely sure they are upright, with their heads pointing up. Out in space, their two ups point in nearly opposite directions. One person's up is very close to the other person's down. And both of them are right. Up has already stopped being a single shared direction, even here on the one surface we all live on. Float a little way out from the Earth, where the pull grows faint, and up and down come loose completely. An astronaut drifting in orbit can tumble slowly head over heels, and at no point is she upside down, because there is no right way up to be. Two astronauts can hang facing each other, each one's head toward the other's feet, and both are correct. Neither one is upside down. There is no floor in the room for them to be upside down against. Out there, up and down are not facts about space. They are leftover habits from growing up on a planet. And it runs further than that. Point a telescope at a distant galaxy, and it might look perfectly upright to you. Someone watching from another corner of the universe would see that very same galaxy lying on its side or tipped right over. And there is no judge anywhere who can rule on which of you is holding it the right way. The galaxy has no top. The universe has no ceiling. Space simply does not come with an up built into it. Which leaves anyone who studies the sky with a real problem. To talk about what is above the solar system, or below it, you first need an up and a down to point at, and space flatly refuses to hand you one. So astronomers did the only thing they could. They invented one. They took the same flat disk the planets travel in and decided to treat it as the floor. Everything poking out of one face of that disk, they call above. Everything out of the other face, they call below. It is a choice, a useful choice, but a choice. Nothing physical is holding that line in place. It works a little like sea level back on Earth. The sea is not the true bottom of anything. It is just a smooth, agreed line that everyone measures from, so that one person's mountain and another person's valley can be compared with the same ruler. The flat plane of the planets is the solar system's sea level, a shared zero line drawn through the middle, so we can finally say how far above or below it any object sits. The difference is that sea level is held in place by gravity and water. This line out in space is held by nothing at all. It exists only because we agreed to draw it. And the line itself is something you have already seen with your own eyes. You just never knew it had a name. On any clear night, the sun went down along a certain path. Later, the moon followed nearly that same path across the sky, and the bright planets, Venus, Jupiter, Saturn, drifted along the very same curve. They were not scattered randomly across the dark. They were all riding the same flat plane, seen from inside it, traced out as one single line arcing over your head. Every time you have looked up and noticed the moon resting close beside a bright planet, you were staring straight along the edge of the disk you live in. Astronomers have a name for that line. They call it the ecliptic. It is nothing more than the flat plane of the planets, viewed edge-on, from a seat inside it. The planets keep to that line in the sky for the same reason they keep to the plane out in space. They were all born in one disk, and they have never left it. So the faint curve you have watched your whole life, without ever thinking twice about it, is the floor of the solar system, drawn across the night. Now the mystery turns inward, because even this floor is not quite what it seems. When astronomers needed a reference plane, the easiest one to reach for was the plane of the Earth's own orbit, the one we happen to ride. The catch is that the Earth's orbit is not the true center line of the solar system. Every planet is tilted a little differently, and the real balanced middle is a kind of average of all their orbits put together. Mercury rides a bit steeper, tilted about 7 degrees. Pluto, far out toward the edge, leans nearly 17, rising well above the plane and dropping below it. Most of the rest sit closer in. And that true average plane leans most toward the heaviest planet, because the heaviest planet counts for the most in the average. The heaviest by far is Jupiter. So the genuine flat center of the solar system bends toward Jupiter's orbit, not toward ours. Our own orbit is tilted away from that true plane by only a little, a bit over 1 degree. 1 degree is almost nothing. A picture frame hung a single degree off level would look perfectly straight to you from across the room. And yet it means the floor we measure everything against, the up and down we use for the whole solar system, is itself slightly crooked. We are standing on a plane tilted a hair from the real one, calling our slightly off direction up and measuring the entire sky against it. What gets me is how ordinary the word feels in our mouths. We say up as though the universe keeps one ready for us. It does not. Up is not something space handed us. It is something we built out of need from the plane we happen to be standing in. And even our building came out a little crooked, leaning gently toward a giant planet we never thought to ask. There is no up out there. There is only the up we pointed to and agreed to call by that name. We have aimed straight out of the plane and said, "That way is up." We have admitted it is a choice, and even a slightly tilted one. None of that answers the single thing we actually want to know. When we finally turn and look along that invented direction, straight out of the flat world we were born into, what is really out there waiting? So we turn at last and look straight up out of the flat plane, ready for whatever has been hiding up there. And the first thing we find is dust. Not up in the clean direction, as it happens, but all around us, spread thin across the very plane we are trying to leave. The planets formed inside a disk of gas and dust, and that disk, we said, was blown away long ago. That is true of the gas. A faint haze of fine dust never fully left, though. It still hangs in the plane of the planets, thin as smoke, circling the sun right alongside the worlds. Where does it keep coming from if the sun cleared the place out billions of years ago? It is made fresh, slowly and endlessly, by the ordinary wear and tear of the solar system. Out between Mars and Jupiter, asteroids drift in their millions, and now and then two of them collide and grind each other into smaller and smaller pieces, down to grains finer than sand. Comets feed it too. When a comet swings in close to the sun and warms, it sheds a long trail of dust behind it. And far out in the cold, icy bodies crumble slowly and give off their own faint contribution. All of it drifts inward and settles into the same flat plane, because nearly everything that makes the dust already lives in that plane. That dust does not just sit there quietly, though. It is caught in a tug-of-war between two forces. The sun's gravity pulls every grain inward, trying to hold it in orbit. The sun's light pushes every grain outward, with the faint, steady pressure of sunlight itself. Which force wins comes down entirely to the size of the grain. For the very smallest specks, finer than smoke, the push of light beats the pull of gravity, and those grains get blown straight out of the solar system, never to return. The larger grains are too heavy for light to shove away, so gravity keeps them. And the ones in between live out the strangest fate of all. Picture running through falling rain. Even when the rain is coming straight down, the moment you run, it seems to slant into your face as if it were falling from somewhere ahead of you. A grain of dust orbiting the sun feels exactly this with sunlight. Because the grain is moving sideways along its orbit, the sunlight seems to arrive slightly from the front. And light coming from the front pushes gently backward against the grain's motion like a faint headwind. That tiny, constant headwind bleeds away a little of the grain's orbital energy, year after year, until the grain spirals inward, circling closer and closer to the sun, and finally falls in and is gone. Physicists worked this out about a century ago, and it still carries the names of the two men who described it, the Poynting-Robertson effect. A grain caught in it does not last forever. It has a deadline. The same clock runs on the whole haze, not just on single grains. Left alone, the entire band of dust we see would drain into the sun in a cosmic blink, a few tens of thousands of years, nothing at all beside the 4.5 billion years the solar system has existed. If the dust is still here, it can only be because it is being replaced as fast as it is lost. What hangs in the plane is not an ancient relic, it is a fountain. Old dust forever spiraling down into the sun, fresh dust forever arriving from shattered asteroids and crumbling comets to take its place. The disk of dust is billions of years old as a shape, and only thousands of years old as actual grains. Dust has one odd quality. You only ever see it when light catches it. Think of a dark room with the curtains nearly shut and one thin beam of sunlight slipping through the gap. In that beam, all at once, you can see them. Countless tiny specks hanging in the air, lit up, drifting. They filled the whole room the entire time. You simply could not see them until the light struck them at the right angle. The dust spread through the plane of the solar system behaves the same way. Sunlight strikes those countless grains, scatters off them, and that scattered light is faint, but it reaches us. And you can see it, with your own eyes, on the right night. Get far from any city, on a very dark and clear night, and look toward the horizon just after the last of the sunset has faded, or just before the first trace of dawn. If the night is dark enough, you will catch a soft, pale cone of light leaning up from the horizon, faint as smoke, tilted along the same line the sun and planets follow. That glow is called the zodiacal light. After the zodiac, the band of constellations strung along the ecliptic, the same line the planets walk. It is not a glow in our own air. It is not the last of the sunset, and it is not the northern lights. It is sunlight, scattering off the dust of the whole solar system, coming back to your eyes. There is a second glow, even fainter, and it hides in a stranger place. Look at the point in the sky exactly opposite the sun, the part of the night nearly overhead around midnight, and on the very darkest nights, a dim oval patch of light rests there. It is called the Gegenschein, the counterglow. It is the same dust, seen this time looking straight away from the sun, where the grains throw sunlight back at us the way a road sign flares in your headlights at night. Two faint glows, then, one leaning off the fading sunset, one hovering opposite the sun at midnight, both of them the same flat sheet of dust, simply lit from different angles. I never quite get over the fact that you can see it at all. Most of the time, the solar system is an idea, a diagram in a book, a thing you take on trust. That pale cone of light is the actual disk you live in, made faintly visible, hanging right there over the hills. For a few minutes, in the right darkness, you are not imagining the plane. You are looking straight down the length of it. We have done more than look, as well. Spacecraft crossing the solar system carry small detectors that register each grain of this dust as it strikes, one tiny impact at a time. And buried inside the broad haze, those measurements and the infrared glow of the dust reveal faint bands, slightly brighter rings that trace back to specific families of asteroids which shattered long ago. The haze is not featureless. It carries the fingerprints of ancient collisions, written in rings around the sun. Now notice which way all of this light leans. It clings to the ecliptic, the line of the planets, and fades fast on either side of it. Because the dust is packed into the plane and thins out quickly above it and below it, just as the planets do. The further from the plane you look, the less dust lies between you and the stars. And that quietly turns the whole picture around. Look sideways, out along the plane, and your line of sight runs through the full length of all that dust, lit and scattering, smudging everything behind it. Look straight up, out of the plane, and your line of sight passes through almost none of it. It is like a city smothered in haze. Stand on a street and look down its length, and you peer through mile after mile of thick air until the distance dissolves into a blur. Look straight up, and you cut through the thinnest possible slice of that same haze into clear sky. The plane is the hazy street. Straight up is the clear sky overhead. So the direction with the least in it turns out to be the most valuable direction to look. The cleanest view of the rest of the universe, from anywhere inside our solar system, lies straight up out of the plane and straight down beneath it. The disk that gives us a home, that holds the earth and the sun and all the warmth and light, is also the very thing fogging our view of everything beyond it. Our home and our haze are the same flat sheet of matter. And we do not watch this dust from any safe distance. We sit inside it. It fills the space between the earth and the sun, and we move through it every single day. One thing needs straightening out, though. Clean is not the same as empty. Look up out of the plane and you pass through very little dust, true. But you are not staring into a perfect void either. Something does surround this entire solar system, reaching out in every direction at once, including the two directions the planets never travel, straight up and straight down. And unlike the planets, unlike the dust, unlike everything we have looked at so far tonight, it is not flat in the slightest. It does not lie in the plane. It wraps around us like a shell. So if our whole world is a flat disk, what is this round thing enclosing it? The thing that pays no attention to the plane at all. The round thing enclosing us has a name. It is called the Oort Cloud, and it is the largest structure the sun can call its own. Everything we have looked at so far has been flat. The planets, the dust, the pale disk lit up across the night. The Oort Cloud is none of that. It is a vast spherical shell of frozen worlds wrapped around the entire solar system in every direction at once. Above the plane, below it, off to every side, a great hollow ball of ice, with the sun and all its planets resting at the very center. To feel how far out this shell sits, follow a single beam of sunlight. Light leaves the sun and reaches the Earth in about 8 minutes. That same light, racing on at the fastest speed anything can travel, reaches Neptune, the outermost planet, in roughly 4 hours. To reach the inner edge of the Oort Cloud, that beam would have to keep going for many more days. And to reach the outer edge, it would travel for more than a year and a half, still moving at the speed of light. The shell stretches so far that it covers a large part of the gap to the nearest other star, by some estimates, a third of the way or more. The planets, beside all that, are huddled in a tiny bright knot right at the middle. The cloud is built from trillions of icy bodies, most of them no larger than mountains, made of frozen water, ammonia, and methane. They are leftovers, the same raw material the planets were built from, the pieces that never got used. Locked inside that ice is a record of what the young solar system was made of, kept frozen and almost unchanged for 4.5 billion years. A deep freeze archive sitting at the edge of everything. They did not form out there in the deep cold, though. That far from the sun, the original material was far too thin to ever build anything. They formed much closer in, down among the giant planets, Jupiter and Saturn and the rest. And then they were thrown away. A small, icy body that wandered too close to one of those giants would get caught by its gravity and flung outward at tremendous speed, like a stone whipped from a sling. Some were hurled so hard they left the solar system forever. Others were flung outward but not quite hard enough to escape, and they settled instead into enormous, slow, looping orbits far beyond the planets. Those are the bodies that became the Oort Cloud. When they were first flung out, their paths still mostly remembered the flat plane they came from. Out at those enormous distances, though, the sun's grip grows weak, and other forces finally get a say. Stars drift past over millions of years, and the combined pull of the entire galaxy tugs gently and endlessly on those far-flung bodies. Across billions of years, those faint outside pulls lifted the orbits up out of the plane, tilted them every which way, and stirred the whole swarm until it lost all memory of the flat disk it began in. The flatness was sculpted away from the outside by the galaxy itself. What was once flung from a disk became a ball, shaped not by the sun, but by everything around it. It is not perfectly even, in fact. The inner part of the cloud, closer to the sun, stayed somewhat flattened, more like a thick donut, where the sun still holds a little sway. The outer part, far enough out for the galaxy to take full control, is a complete sphere. A flattened collar near home, opening into a great round shell at the edge. And no one has ever seen it. The Oort Cloud is too far and too faint for any telescope to show. Every part of it remains, even now, something we know only by its effects. The evidence comes from comets. Every so often a comet appears that takes thousands, even millions of years to circle the sun once on a path that reaches absurdly far out. These long-traveling comets do not arrive along the flat plane, the way the planets and asteroids do. They fall inward from every direction at once, top, bottom, and all sides, tilted at every possible angle. That is the fingerprint of a sphere. A flat source would feed them along the plane. A spherical source sends them from everywhere, and everywhere is exactly where they come from. We may even have caught sight of the cloud's nearest members. Far out past Neptune circles a small, deep red world named Sedna, on an orbit so stretched that a single lap around the sun takes around 11,000 years. It never comes near the planets, and it swings out to distances that belong to no ordinary part of the solar system. Many think Sedna is a body from the inner edge of the Oort Cloud, our first faint glimpse of the great shell, caught at the one brief stretch of its enormous orbit when it drifts close enough to see. The same passing stars and galactic tides that shape the cloud are still stirring it. Now and then, a far tug nudges one of those frozen bodies just enough to shake it loose, and it begins the long fall toward the sun. Thousands of years later, it arrives in our skies as a comet. The great comets that appear maybe once in a human lifetime, hanging in the dark with a long pale tail, are visitors from this outer shell. If you have ever stood outside and watched one, you were looking at a piece of the Oort Cloud, a chip of the solar system's frozen edge, fallen close enough to catch the sunlight. And for all those trillions of bodies, the Oort Cloud is almost unimaginably empty. The shell is so enormous that its members are spread, on average, tens of millions of kilometers apart. All of them together may add up to only a handful of Earth's worth of material, scattered across a volume the mind cannot really hold. If you were set down somewhere inside it, you would most likely see nothing at all. No glittering field of ice, no crowded swarm. Just the distant sun shrunk to a single bright star, and the dark. You could fly straight through the entire cloud and never pass close to one of its worlds. This shell is, in a real sense, the true edge of the sun's family. Out here, the sun's hold has grown so faint that the comets are barely kept at all. A star passing close enough can peel some of them away, and across its long life the sun has almost certainly lost comets to other stars, and perhaps captured a few of theirs in return. The outer Oort Cloud is less a fixed wall than a slow, shifting borderland, quietly traded back and forth with the rest of the galaxy. It unsettles me a little that the largest thing belonging to our sun is the one piece of it no one has ever actually seen. We have close photographs of Pluto, detailed maps of Mars, sharp pictures of the rings of Saturn. The cloud that marks our real outer border, the shell that shows where the sun's reach finally gives out, we know only from the comets that drop out of it. It is the most certain thing we cannot point a camera at. The Oort Cloud, for all its size, is made of cold, passive debris, frozen leftovers, drifting in the dark, doing nothing but waiting. There is another boundary around us, far closer in, and it is nothing like this one. It is not made of objects at all. It is made of the sun itself, reaching outward, pressing against the space between the stars. And unlike the Oort Cloud, which no spacecraft has come close to crossing, this other edge is one we have actually reached and passed through and watched our machines fall silent on the far side of. So the sun, it turns out, has more than one edge. What is this second boundary, the one made not of frozen leftovers, but of the sun's own breath? The sun is breathing out. Not air, and not gently. From its blazing outer layers, the sun is constantly flinging a thin stream of its own material out into space, in every direction, without pause. This stream is called the solar wind, and it has been blowing for as long as the sun has burned. It is not ordinary gas. It is plasma, a haze of broken atoms, electrically charged particles ripped apart by the sun's ferocious heat, mostly the lightest pieces, racing outward. The wind leaves the sun at something like 400 kilometers every second, and in its fastest streams, nearly twice that. At that speed, a particle of solar wind crosses the whole distance from the sun to the earth in just a few days. Stranger still, the wind is launched from the sun's outer atmosphere, the corona, which burns at over 1,000,000 degrees, far hotter than the sun's own surface lying beneath it. Why that thin outer atmosphere is hundreds of times hotter than the surface below is a puzzle physicists still have not fully solved. Whatever the cause, that searing heat is what gives the wind the speed to tear away from the sun's gravity and escape into space. The sun loses a little of itself this way, every second, forever. The amount is tiny next to the sun's enormous bulk, so it will keep doing this for billions of years more without running low. And as the wind streams outward, it carries something invisible with it. The sun's magnetic field, stretched out and dragged along, threaded all through the wind like dye trailing in a current. So the sun is not only throwing out particles, it is extending its own magnetic reach across the entire solar system, far past the planets. All that outward rushing wind does one enormous thing. It blows a bubble. Pushing out in every direction at once, the solar wind clears itself a vast, roughly rounded cavity in the thin gas drifting between the stars. That cavity is called the heliosphere, and it is the second edge of the sun, the one made of the sun's own outpouring rather than of frozen debris. Notice what kind of shape it is. Not flat, not a disk. The wind blows up and down and sideways with the same force, so the bubble swells in every direction, above the plane and below it just as much as along it. After all the flatness of the planets and the dust, the sun finally makes something round. The bubble has an outer skin, of a sort, and it forms where two pressures meet. From the inside, the solar wind pushes outward, always trying to expand. From the outside, the gas and dust that fill the space between the stars push back. Where those two pressures finally balance, the solar wind can travel no further, and it stops. That balance point is the real boundary of the bubble, and it has a name: the heliopause. Cross it, and you have left the region ruled by the sun's wind and entered the open space between the stars. It is not a tidy sphere, though, because the sun does not sit still. The whole solar system is drifting through the interstellar gas, slowly plowing forward into it. Picture walking forward on a breezy day while holding a big soap bubble in front of you. The breeze presses the bubble flat on the side facing into the wind and lets it trail out long and soft behind you. The heliosphere does the same. It is squashed on the side facing the way we are moving and drawn out into a kind of tail on the side behind. A rounded nose ahead, where the sun pushes into the oncoming gas, and a long wake stretching away behind. The exact shape of that tail is argued over to this day, and we will come back to why no one is certain. Long before a probe reaches the outer skin, something abrupt happens to the wind itself. For most of its journey, The solar wind blows outward faster than its own pressure waves can travel. A smooth, fast, supersonic flow. Then, at a certain distance, it runs into the pressure of the gas ahead and slows down all at once, dropping below that speed and turning thick and turbulent. You can watch this exact thing happen in a kitchen sink. Turn the tap on and look where the water strikes the flat bottom. Right under the stream, it races outward fast and thin and smooth. Then, at a certain ring, it suddenly jumps up into a thicker, churning band. That ring is where the fast water abruptly slows, and the solar wind does the very same thing, far out in space. The place where it happens is called the termination shock, and beyond it lies a wide, turbulent zone of slowed wind before you ever reach the true edge. We know all of this is really out there because 2 spacecraft have flown through every layer of it. Voyager 1 and Voyager 2 launched back in 1977, before most people listening tonight were born, and they have been flying outward ever since. They crossed the termination shock, that turbulent slowing of the wind, and pushed on through the churning zone beyond it. Then, in 2012, Voyager 1 crossed the heliopause itself and slipped out into interstellar space. Voyager 2 followed in 2018. They are the first 2 things ever built by human hands to leave the sun's bubble completely. How did we even know they had crossed? The signs arrived together. The familiar solar wind particles around each craft thinned away almost to nothing. The count of cosmic rays, the high-energy particles that pour in from the wider galaxy, jumped sharply upward now that the bubble was no longer holding them back. And the direction of the magnetic field shifted from the sun's own field to the field of interstellar space. There was one more clue, and it is my favorite. Voyager 1 carries an instrument that listens to the faint ringing of the plasma around it, and the pitch of that ringing depends on how dense the plasma is. Out beyond the heliopause, the ringing rose to a higher pitch because the gas between the stars is denser than the thin wind inside the bubble. A small, rising tone sent back across billions of kilometers, telling us our machine had crossed into a different sea. And notice how close this edge is, set against the last one. Light reaches the heliopause in about 17 hours. The outer Oort Cloud, remember, was more than a year and a half away at that same speed. So the sun's wind bubble is small. It sits deep, deep inside the great frozen shell, like a single lit room inside an enormous dark house. 2 edges then, wildly different in size. An inner edge of the sun's breath, an outer edge of the sun's frozen leftovers, with everything we have ever known nested inside both. This bubble is not only a curiosity, it is a shield. The galaxy is full of cosmic rays, fast and damaging particles flung out by distant exploding stars, and the heliosphere holds most of them back. The wind and the tangled magnetic field deflect the bulk of that radiation before it can ever reach the planets. The sun, simply by breathing out, wraps a protective shell around its whole family, including the small blue world where you are lying right now. And out past that shell, the 2 Voyagers are still drifting, still faintly whispering back, carrying their golden records into a dark they will never return from. The boundary, in the end, is not a wall at all. It is a standoff, a truce between 2 winds, the sun's blowing outward and the galaxies pressing inward, holding the line wherever their strengths happen to match. And we would not know where that line sits, or even that it sits anywhere, if not for 2 machines that drifted far enough out to feel it. Step back, though. and a question hangs over the whole bubble. The wind that blows it open has to come from somewhere on the sun, and it does not blow evenly. The fastest, strongest, steadiest wind of all does not pour out of the sun's middle. It streams from the top and the bottom, from directly above and below the sun. Why would the sun's strongest breath come from its poles? The answer begins with something the sun is wearing that you cannot see. The sun is not simply a ball of fire. It is a ball of fire wrapped in a powerful, tangled magnetic field, and that field reaches up off the surface and out into the corona, the sun's thin outer atmosphere. The wind is plasma, and plasma is made of charged particles, and charged particles are not free to wander wherever they please. They are forced to follow magnetic field lines, like beads threaded along a wire. So the question of where the wind escapes is really a question about the shape of the sun's magnetic field. Over most of the sun's surface, that field loops. A magnetic line rises out of the surface in one spot, arches up into the corona, and dives back down into the surface nearby, making a closed loop like the arc of a fountain. Plasma caught on those loops is trapped. It rises along the arch, slides back down the far side, and never gets away. These closed loops are what make the bright, looping shapes you can see around the sun's edge during a total eclipse, and they hold most of the sun's outer atmosphere firmly in place. Where the field loops, the wind is mostly bottled up. In some places, though, the field does not loop back. Instead of arching over and returning to the surface, the magnetic lines reach straight up and out, opening into space and never coming back down. Along those open lines, the plasma is no longer trapped. It streams freely outward, straight off the sun and away, with nothing to hold it in. It is the difference between a sealed arch and an open chimney. Over a closed loop, the plasma circulates and stays. Over an open field line, it pours up the chimney and escapes into space. The regions where the field opens up like this are called coronal holes. They are not truly holes, and they are not empty. They look dark in ultraviolet pictures of the sun only because the escaping plasma leaves them thinner and cooler than the trapped, glowing loops around them. Dark, here, just means the gas has streamed away. And during the sun's quiet years, the two largest and most stable coronal holes sit squarely over the poles. One open chimney at the top of the sun, one at the bottom, each yawning open for years at a time. That is the answer to where the strongest wind comes from. Out of those wide polar openings pours the fast solar wind, streaming away at 700 to 800 kilometers every second. Down near the equator, where the field mostly loops and the wind has to leak out around the edges of closed regions, the wind is slower, 300 to 500 kilometers a second, and far messier. The polar wind is fast, steady, and smooth, a clean, broad current. The equatorial wind is slow, gusty, and tangled, forever shifting. The sun's calmest, most powerful exhale comes from its top and its bottom. Its restless, turbulent breath comes from its waist. And the two winds do not only differ in speed, they are made of subtly different stuff. The slow wind, which lingers inside those closed loops before it leaks out, emerges with certain elements enriched, changed by its long stay in the trapped corona. The fast wind, escaping straight up the open chimneys with no time to linger, carries a makeup much closer to the raw surface of the sun. The difference is small, but it is real, and it can be measured. When a gust of wind reaches a spacecraft, scientists can read its chemistry almost like a return address and trace it back to whether it came from an open polar hole or a closed equatorial loop. There is one more thing the spinning of the sun does to all of this. The wind flies straight outward, but the sun is turning underneath it once every 20-some days. Think of a lawn sprinkler spinning as it throws water. Each drop flies out in a straight line, but because the nozzle keeps rotating, the stream as a whole bends into a spiral. The solar wind does exactly this. Each parcel races straight out, but because the sun rotates as it launches them, the magnetic field threaded through the wind gets wound into an enormous spiral, wrapping outward through the entire solar system. The sun's magnetic reach is not a set of straight spokes, it is a vast pinwheel. And running through that pinwheel is the single largest structure in the whole solar system, one almost no one has ever heard of. The sun's magnetic field points one way out of the north and the opposite way out of the south. Somewhere between them, those two halves must meet, and where they do, they form a thin dividing surface, a sheet, separating the north-pointing field from the south-pointing field. Because the sun spins, that sheet is wound into the same great spiral as the wind, and because the sun's magnetic axis is usually tilted a little, the sheet is not flat. It ripples up and down as it turns. Picture a ballerina spinning, her skirt flaring out around her, the hem rising and dipping with every turn. That is the shape of this sheet, twirling outward past all the planets, its rippling hem sweeping above and below the plane. It is called the heliospheric current sheet, and it is wider than the orbit of every planet. When the sun is calm, that skirt hangs almost flat along its equator. When the sun grows active, the skirt tilts and crumples, its hem climbing steeply toward the poles. The sheet has a kind of mood, and it shifts slowly across the years. And the Earth lives right inside the flare of that skirt. As the sheet ripples past, our planet crosses from one side of it to the other and back again, several times every month, slipping between the north-pointing field and the south-pointing field. Each crossing gives the magnetic world around the Earth a small nudge. And when a fast stream from a polar coronal hole catches up and rams into the slower wind ahead of it, the pileup can rattle our magnetic field harder, and on those nights the auroras flare brighter and reach further from the poles. So if you have ever watched the northern lights ripple green across a winter sky, part of what you were seeing was the sun's polar wind, the breath from straight above the sun, arriving at last at the top of our own world. The sun keeps its cleanest, strongest, simplest behavior in the two places we have the hardest time ever seeing. The wind we know best, the gusty one that batters the earth and lights our skies, is the messy leftover from the sun's crowded middle. The pure, powerful current, the one that shapes the entire bubble we live inside, blows from the poles, where we have almost never looked. But open chimneys over the poles are only the surface of the story. They are a symptom, not a cause. Something has to decide that the field will loop shut around the equator and tear open at the poles. Something has to arrange that pattern, hold it steady for years, and then, as we will find, pull it all down and build it back in reverse. All of that is decided in the one part of the sun we have barely glimpsed. So what is really happening at the top and the bottom of the sun, quietly running the behavior of the entire star? To find the engine, you have to stop picturing the sun as solid. The Earth turns all in one piece. The ground at the equator and the ground near the poles swing around together, one full turn a day, locked to each other because the Earth is rock. The sun is not rock. It is gas and plasma all the way through, and gas does not have to turn as a single body. So it does not. The sun's equator spins faster than its poles. The middle comes around once in about 25 days. The higher latitudes lag behind, taking 34 days or more for a single turn. The sun is forever lapping itself. That uneven spin is the first turn of the engine. Remember that the sun's magnetic field is frozen into its plasma, dragged along wherever the plasma goes. So when the fast equator pulls ahead of the slow poles, it drags the magnetic field with it, stretching the lines out and winding them around the sun, again and again, turn after turn. Picture wrapping a thread around a spinning spool. Every rotation lays down another loop, winding it tighter, storing more and more tension. The sun does this to its own magnetic field for years on end, coiling it up, packing it with strain. A wound-up field cannot stay buried forever. As the coils grow tighter and stronger, twisted ropes of magnetic field turn buoyant, lighter than the plasma around them, and they begin to rise. A rope of field floats up through the sun and bursts through the surface in two places, poking out and arching back in, like the top of a buried loop pushing up through the skin. Those two breakthrough points are a pair of sunspots. Sunspots look dark, not because they are cold in any ordinary sense, but because the intense magnetic field there chokes off the heat rising from below, leaving those patches cooler and darker than the blazing surface around them. Every sunspot is the visible footprint of that wound-up field forcing its way out. And the spots do not appear just anywhere. They trace a pattern, repeated every cycle, that took astronomers years of patient record-keeping to uncover. Early in each cycle, the first sunspots break out at high latitudes, far from the equator. As the years pass, new spots appear closer and closer to the equator, marching steadily down toward the middle until the cycle ends and the whole pattern begins again near the poles. Chart the spots over time, latitude against year, and they draw two wings sweeping in toward the center, a shape so distinctive it earned a name: the butterfly diagram. The sun has been drawing that same butterfly cycle after cycle for as long as we have kept watch. Now the poles take their turn. Each sunspot pair emerges slightly tilted, and across the cycle, a slow current of plasma at the surface carries the trailing half of all those pairs gradually up toward the poles. There is a conveyor belt inside the sun, a vast, slow circulation that flows from the equator toward the poles along the surface, sinks deep down, and creeps back toward the equator far below. Riding that belt, magnetic field of one particular sign drifts poleward, year after year, and piles up at the top and bottom of the sun. The field it carries is the opposite of whatever is already sitting at the poles, so as it arrives, it cancels the old polar field, wipes it away, and then rebuilds it pointing the other direction. That is the reversal. Roughly every 11 years, the sun's north and south magnetic poles trade places. What was the north becomes the south, and the south becomes the north. It takes a full 22 years for the field to flip and then flip back to where it began, one complete magnetic heartbeat of the sun. And the two poles do not always switch at the same moment. One can lead the other by months, even a year or two, so that for a while, the sun has no clean north and south at all, its field briefly scrambled before it settles again. So the poles are not quiet caps on a busy star. They are where the whole cycle comes to rest and turns over. And they hold something more remarkable still. They hold the sun's memory of what is coming. The strength of the field gathered at the poles when the sun is quietest turns out to forecast how fierce the next round of sunspots will be, 11 years later. A strong polar field now means a stormy sun a decade from now. A weak one now means a mild one. The future of the sun's activity is written, faintly, at its poles, years before it ever plays out across its face. For centuries, we have watched the sunspots come and go, the flares erupt, the surface seethe, and we called all of that the sun's activity. We were watching the smoke and calling it the fire. The fire is the wound-up field, the conveyor belt, the slow reversal at the poles. The spots and the flares are only the smoke escaping where the engine vents. And the engine room sits at the two ends of the sun we can barely see. You might wonder how anyone can speak so confidently about a conveyor belt buried inside a star no one has ever cut open. The answer is that the sun rings. Sound waves bounce around inside it endlessly, trapped, and they make the whole surface tremble in millions of tiny patterns, rising and falling by small amounts. By watching that trembling with great care, scientists read the speed and depth of the layers inside, the same way a doctor reads the inside of a body with ultrasound, or the echoes of an earthquake reveal the structure deep within the earth. That listening has traced the sun's inner spin and pinpointed a thin, restless layer far down, where the churning outer region meets the calmer interior. That shearing layer is widely thought to be where the dynamo truly lives, where the field is wound tightest before it rises. And the engine does not always run at the same pace. Now and then, across the centuries, it nearly stalls. In the 1600s, the sun fell unusually quiet for about 70 years. Sunspots almost vanished from its face, and the steady 11-year beat faltered. That long lull lines up with a stretch of bitterly cold winters across Europe, when rivers that rarely froze, like the Thames in London, froze hard enough to hold fairs out on the ice. Just how much the quiet sun cooled the earth is still argued over, but the timing is hard to wave away. These deep century-long lulls seem to trace back, once again, to a weakness in the polar field, held across many cycles. The sun keeps its longest moods at its poles. You have lived through several of these flips already, without feeling a thing. Every 11 years or so, while you went about your ordinary days, the sun quietly tore down its entire magnetic field and built it back in reverse. And nearly everything we have just traced, the uneven spin, the wound-up field, the butterfly, the reversal, the buried conveyor belt, we have pieced together almost entirely from the side. From within the flat plane, staring at the sun's equator, having barely once looked straight down at a pole, where the whole story begins and ends. We have reconstructed the engine without ever once standing over the engine room. So why, out of all the places we have sent our machines, have we almost never gone to the one direction that would let us look the sun's poles in the face? The reason is not distance. The poles of the sun are not far away. They sit at the top and the bottom of the sun, no farther from us than the rest of the sun is, a little over 8 minutes away at the speed of light. We have sent machines billions of times farther than that. The reason we have almost never looked at the sun's poles is not how far they are. It is how fast we are already moving, and in the wrong direction. Go back to that sideways motion from the very start of tonight. The Earth is racing around the sun right now at about 30 kilometers every second. That is a little over 100,000 kilometers an hour, faster than any rifle bullet, far faster than any spacecraft we have ever launched under its own power. Every second, you and the whole planet sweep 30 kilometers sideways around the sun, roughly the width of a large city, gone in a single tick of a clock. And when a rocket lifts off from the Earth, it does not start from rest. It is already moving at that same 30 kilometers a second sideways because it was sitting on a planet that was... Most of the time, that inherited speed is a gift. If we want to reach Mars, we do not have to build that speed from nothing. We already have almost all of it. The rocket only needs to nudge its existing sideways motion a little, adding a few kilometers a second in the right direction, and the sun's gravity does the rest, carrying the spacecraft out along a long, curving path to another world. Going outward, to the planets, mostly means working with the motion we were born with. Now try to go straight up out of the plane. All at once, that same sideways speed becomes the enemy. To climb out of the plane, a spacecraft first has to get rid of the 30 kilometers a second it already carries sideways, cancel it completely, and then build brand new speed in the perpendicular direction, pointing up and out. Think of standing on a fast spinning carousel. Stepping over to a horse beside you, moving along with the spin, is easy, but trying to walk straight off the edge, sideways to all that motion, throws you hard because your body is still carrying the full speed of the spin. To leave cleanly, you would first have to kill all of that motion. The solar system is that carousel, turning for 4.5 billion years, and everything on it carries the spin. Spaceflight has a word for the budget of speed change a spacecraft can spend, the total it can muster from its own engines and fuel. They call it delta V, and it is the real currency of the solar system. Every maneuver costs some. Once a spacecraft has spent its budget, it can do nothing more. And the prices tell the whole story. Climbing from the ground into orbit around the Earth costs about 9 or 10 kilometers a second of that budget. Going on from there to Mars costs only about 4 more. To Jupiter, around 6.5. These are all comfortably within what our rockets can do. Going straight up out of the plane, though, costs something near 30 kilometers a second because you have to erase Earth's whole sideways motion and build a new one. That is more than any chemical rocket has ever delivered to a single spacecraft. The largest deep space missions ever flown carried budgets of perhaps 15 to 20 over their entire lifetimes. The straight climb out of the plane is not a little beyond reach. It is wildly beyond it. This leads to one of the strangest rankings in all of spaceflight. Reaching Pluto, out on the far rim of the planets, billions of miles away, costs less than reaching a point just a few million miles straight above the sun's north pole. The faraway icy world is the easy target. The empty patch of sky right over the sun is the hard one. It comes down to the shape of gravity. To go outward, you only add a little to the motion you already have, and the orbit gently stretches into a long ellipse that coasts all the way out to Pluto. The sun's gravity does the traveling. Going out is downhill. To go up, none of your existing motion helps, and the sun's gravity does not pull you up there either, because gravity points inward toward the sun, never up out of the plane. Every single kilometer a second of upward speed has to be bought outright with fuel. Going up is a sheer cliff. You might think the fix is simply to build a bigger rocket. It is not, and the reason is buried in the cruel arithmetic of rockets themselves. To go faster, a rocket needs more fuel. But that extra fuel has weight, so now the rocket needs still more fuel just to push the added fuel, and that fuel needs fuel of its own, and it snowballs. It is like packing food for an enormously long hike with no resupply. The meals you will eat on the last day must be carried the whole way, and carrying them means packing still more food to fuel the carrying until the pack grows impossible. Past a certain point, adding fuel barely buys any extra speed at all, because nearly all of it goes into lifting the fuel. The 30 kilometers a second needed to climb straight out of the plane sits on the far side of that wall. No reasonable rocket can simply muscle through it. And the trap is invisible, which is what makes it so easy to forget. You are moving at 30 kilometers a second this very moment, lying perfectly still. You cannot feel it. You never could. Because the room, the air, the earth, and everything you have ever touched are all moving along with you at exactly the same speed, in exactly the same direction. The very smoothness that hides the motion is the thing that makes it so costly to break out of. We are not held down by any wall. We are held by a speed so steady and so shared that it feels like perfect stillness. It is a strange kind of prison, one with no bars, no walls, no locked door. It is built entirely out of motion we cannot feel, inherited from a spinning cloud that flattened before the Earth even existed. The plane is endlessly generous to anything content to travel within it, and merciless to anything that tries to leave. And the one view we most want, the look straight down at the sun's poles, lies on the far side of all that mercilessness. And yet it has been done. Not once, but twice, human machines have climbed up out of the plane and turned to look back toward the poles of the sun. They did not do it by brute force. No rocket could ever pay that bill. They did it by cheating the geometry, by borrowing speed from somewhere other than their own fuel tanks. So if no rocket can simply climb out of the plane, where did the missing 30 kilometers a second come from? The missing speed did not come from a bigger rocket. It came from the planets themselves. There is a trick, and it is the closest thing in all of physics to getting something for nothing. A spacecraft can fly close past a moving planet, let the planet's gravity catch it, and swing it around, and come away moving faster or slower, or pointed in a completely new direction without burning a single drop of fuel. It is called a gravity assist, and almost every long journey through the solar system has leaned on it. The way it works is easier to feel than it sounds. Picture throwing a rubber ball at the front of a moving truck. The ball strikes the truck and bounces off, and because the truck was driving toward it, the ball comes back faster than you threw it. It stole a little speed from the truck. The truck, being so much heavier, slows by an amount far too small to ever notice. A spacecraft swinging past a planet does the same thing, except nothing actually touches. Gravity does the bouncing. The craft borrows a sliver of the planet's motion, and the planet loses a sliver of its own, so tiny it would take longer than the age of the universe to matter. And a heavy enough planet, caught at the right angle, can do more than speed a spacecraft up. It can throw it clean out of the plane. Swing past a giant the right way, and instead of merely going faster, the spacecraft comes away tilted, climbing up out of the flat world, the planet's share. That borrowed push, free of charge, is the only thing that has ever lifted a machine above the sun. The first to do it was a spacecraft named Ulysses, a joint mission of the American and European space agencies, launched in 1990. Its goal was the sun's poles, and the way it got there is one of the strangest journeys ever flown. To reach the top and bottom of the sun, Ulysses did not head for the sun at all. It flew in the opposite direction, all the way out to Jupiter. Out past the asteroid belt, in 1992, it swung close around the giant planet and let Jupiter's enormous gravity bend its path by nearly 80 degrees, almost a right angle, hurling it up and out of the plane of the planets. From there, it fell back inward on a steeply tilted orbit, one that carried it high over the sun's north pole and then deep beneath its south. Think about what that means as a route. To look at the poles of our own star, the closest star there is, the first thing this machine had to do was fly more than a year, and most of 1 billion kilometers, in the wrong direction, out to Jupiter, just to borrow the push it could not buy. There was no other way. The 30 kilometers a second was simply not for sale at any fuel tank. It had to be stolen from a giant. Ulysses worked. For the first time, a machine flew over the sun's poles and measured directly what was there. It found that the fast wind really does stream from the polar coronal holes, exactly where the dynamo picture said it should, and it mapped the magnetic field and the particles across latitudes no one had ever sampled. But there was one thing Ulysses could not do. It carried no camera able to photograph the sun. Built with the instruments of its time, it was a machine of senses without sight. It could feel the poles, taste the wind pouring off them, measure their magnetism. It could never once look at them. We learned what the poles were doing and still had no idea what they looked like. Ulysses fell silent in 2009, after nearly 18 years of flying. But its orbit did not end. Somewhere out there right now, that dead, quiet machine is still looping high above the sun and far below it, tracing the same great tilted circle it earned from Jupiter, carrying no power, sending nothing home. An empty spacecraft on an endless path, the only orbit of its kind, still keeping watch over poles it can no longer see. The second machine to climb out is flying right now. A European mission called Solar Orbiter, launched in 2020, chose a different way up. Instead of one enormous shove from Jupiter, it takes many small ones from Venus. Each time it passes Venus, the planet's gravity tilts its orbit a few degrees higher above the plane, and then it swings around the sun and comes back for another pass, and another, climbing the way you climb a spiral staircase, one patient step at a time. It trades the long detour for years of slow, repeated nudges, gaining height with every loop. And this one carries eyes. Solar Orbiter is built around cameras and telescopes, the very thing Ulysses lacked, designed from the start to look at the sun, not only to feel it. It flies in surprisingly close, nearer than the planet Mercury at its closest approach, sheltered behind a heat shield against the ferocious light, its instruments peering out through small doors. And in just the last stretch of its journey, it has finally climbed high enough to do the thing no machine ever has, to turn its cameras down toward a pole of the sun and take the picture. Very recently, the first real views of the sun's south polar region came home. The first time in all of history that human eyes had something more than a guess about what the top or bottom of our own star actually looks like. The mission is still climbing, aiming for steeper angles in the years ahead, with a fuller view of both poles still to come. What we have so far is a first glimpse, no more. But after thousands of years of never seeing them at all, a first glimpse is an enormous thing. To look at the poles of the nearest star, we flung one machine out to Jupiter and waited years, then let it die up there, still circling. We sent another to loop past Venus again and again, gaining a few degrees at a time, across more than half a decade, just to tilt its gaze. Whole careers were spent on the single quiet goal of seeing our own sun from above. And after all of it, the long detours, the borrowed gravity, the decades of waiting, the first pictures came back, and they held a small surprise. The pole did not look like the sun we thought we knew. The smooth, familiar face we see from the side was not there. Something else was. So what does the top of our own star actually look like when you finally rise above it and look straight down? To understand why the first pictures were a surprise, you have to know why we never had them before. It was not only that climbing above the sun is hard. Even from right here, looking at the sun's poles is like trying to read the top of someone's head from across a room. From inside the flat plane, the poles sit at the very edge of the sun's disk, turned almost completely away from us, squashed into a thin sliver along the curved rim. Whatever detail is up there gets smeared and flattened, crushed into nothing by the angle. For all of human history, the two ends of the sun have been hidden in plain sight, right there on the edge of the disk, and impossible to actually see. We were not entirely blind to them, though. For more than a century, during total eclipses, when the moon covered the sun's bright face and the faint outer atmosphere leapt into view, observers noticed something at the top and the bottom. Fine, delicate brushes of light, fanning out from the poles, curved and combed like iron filings scattered near a magnet. They sketched these polar rays carefully, eclipse after eclipse, and understood that something structured and magnetic lived up there. But they were always seeing it edge on, from the side, a hint of a shape they could never face directly. They had the brush strokes, and never the painting. So we came to know the sun by its middle. The face we have always watched is the equator, and that face has a particular look. Broad, dark sunspots, large organized regions of magnetic field, the great looping arches that erupt into flares. Everything dramatic and familiar about the sun, the spots, the storms, the towering arcs, happens in that crowded middle band. So we naturally assumed the poles were simply more of the same, seen from a worse angle. They are not. When Solar Orbiter finally climbed high enough to look down at the South Pole, the broad sunspots were gone. In their place was something finer and far more chaotic, a scattering of countless tiny magnetic patches, a salt and pepper field of little knots pointing this way and that, with none of the large, orderly structures that rule the equator. The pole was not a calmer version of the middle. It had a completely different texture, busy at a small scale, tangled, restless in its own quiet way. And how can we even see a magnetic field at all, when it gives off no light of its own? The trick is that a magnetic field leaves a fingerprint in the light passing through it. Where the field is strong, it subtly splits and shifts the colors that the sun's gas gives off, and it tilts the way those light waves are oriented. By reading those tiny changes in the light with great care, a spacecraft can measure the strength and the direction of the magnetic field at every single point on the surface, from millions of kilometers away. The same careful reading shows something more: the speed at which each patch of surface is drifting toward us or away. So the very instrument that maps the magnetism also maps the motion. When we say the South Pole was a jumble of opposite polarities, that is something we actually read, point by point, written into the light the pole sent us. Beneath all of that, the whole surface wears the pattern it wears everywhere. The sun's outer layer boils, like the surface of a pot in the moment just before it simmers, broken into countless cells where hot plasma rises in bright centers and cooler plasma sinks down the dark edges. Each of those cells is enormous, often wider than a large country, and there are millions of them at any one moment. And not one of them lasts. Each cell lives only a matter of minutes before it breaks apart, and a new one rises in its place. The entire face of the sun, a ball more than 100 times wider than the Earth, completely renews its skin every few minutes, without pause. Over the poles, that ceaseless boiling carries the small magnetic knots upward and threads them out into space. And from those threads come the plumes. Long, faint streams of plasma reach out from the polar regions, combed straight along the open magnetic field lines like reeds bent in a current. Seen from the side during an eclipse, they are those same polar rays our ancestors sketched, soft and curved. From directly above a pole, they would fan outward in every direction, like spokes from a wheel, or the petals of some slowly turning flower. And these plumes are not decoration. They are the visible roots of the fast wind, the very streams we met earlier, caught at the moment they leave the sun. And the same vantage shows the open chimney itself. By blocking out the sun's blinding disk, the spacecraft can see the faint corona around it, and there, sitting squarely over the pole, is the coronal hole, the wide open region of magnetic field we met before. For the first time, it can be seen face on, a dark crown set on the top of the sun, the very mouth the fast wind pours out of. The thing we had only ever deduced now has a face. But the deepest surprise in those first images was not the texture and not the plumes. It was the timing. The recent view caught the South Pole in the very middle of its great reversal. Remember that every 11 years the sun's magnetic poles trade places, and that the changeover is not instant. For a while, the old polarity and the new one sit side by side at the pole, jumbled together. That is exactly what the pictures showed. Not a single clean magnetic pole, north or south, but a patchwork of both polarities mixed together, the field caught in the act of flipping. We did not simply photograph the engine room of the sun, we photographed it mid-turn, the field tearing itself down and rebuilding in reverse, held still in a single frame. And that messiness is itself a measurement. A pole crowded with both polarities at once is the mark of a sun near the peak of its cycle, with the reversal underway. When the sun is quiet instead, a single clean polarity gathers there, and the strength of that clean polar field is what forecasts how fierce the next cycle will be, years ahead. The pattern of which polarity is winning and how quickly tells us precisely where in the long cycle the sun stands. For the first time, that reading no longer has to be guessed at from the side. It can be taken straight off the pole as it builds. Think about what else that opens. For all the years we worked out the dynamo, the wound-up field, the buried conveyor belt, the reversal at the poles, we did it from the side, by inference, never once watching the crucial step directly. From above, we can begin to watch the slow poleward drift of plasma across the surface, the upper half of that conveyor belt, flowing toward the pole and carrying its magnetic cargo with it. The one hidden step in the whole story of the sun's magnetic life is finally something we can look straight at and follow as it happens. And step back from the science for a moment to the plain strangeness of it. The sun is the most looked at object in the history of the world. Every civilization watched it. Every instrument we ever built turned toward it. We have detailed photographs of the surface of Pluto, of the moons of Jupiter, of galaxies billions of light years away. And until just now, of one whole face of our own star, the top of it and the bottom of it, there was nothing. No photograph, no film, no record of any kind. If you went looking for an image of the sun's pole from before this, you would find none, because none was ever made. The nearest star, the one that gives us every single day and every harvest, kept one face turned away from us for the entire span of human history until a single machine climbed high enough, just recently, to finally look. We did not catch the pole sitting still, posing for its first portrait. We caught it in the middle of changing into something else. The first time we ever truly saw the top of our own sun, it was already turning itself inside out. And yet, for all of that, what we have is still only a glimpse. Solar Orbiter does not hover over the pole. It sweeps past on its tilted loop, gathers what it can during the brief stretch when its path runs high enough, and then falls back toward the plane as the orbit carries it down again. No machine has ever held still above a pole and simply watched, season after season, the way we would need to in order to truly understand it. And the poles are not even the only prize waiting up there. To get a real, lasting view, we would need a far better way to climb than flinging a probe out to Jupiter and waiting most of a lifetime. So, is there a cleverer way up? Some way to climb out of the plane that does not cost a giant planet and a decade of patience? There is a cleverer way up, and the first time you hear it, it sounds completely backwards. To climb out of the plane, up and away from the sun, the trick is to first dive straight down toward the sun. Fall inward, the wrong direction entirely, before you ever try to rise. It seems like nonsense. It is one of the most elegant ideas in all of spaceflight. The whole thing rests on a single fact about rockets that is easy to miss. A burst from a rocket engine does not always buy the same amount of energy. The faster the spacecraft is already moving when it fires, the more that same burst is worth. The identical engine, the identical fuel, burned for the identical few minutes, adds far more energy to the journey if the craft is racing than if it is crawling. Go twice as fast, and a moving object does not carry twice the energy. It carries 4 times as much. Speed counts double. Think of pushing a child on a swing. To send them higher, you do not push at the very top, where they hang for an instant, barely moving. You push at the bottom, in the rush, where they sweep past you fastest. The very same push, given at top speed, adds far more height than it ever would when they are nearly stopped. Burn your engine where you are moving fastest, and the fuel does the most work it can possibly do. That is the whole secret. Now ask where in the entire solar system a spacecraft moves fastest. The answer is deep down, close to the sun. It is the same as a ball let go at the lip of a deep valley. The deeper the valley, the faster the ball is moving by the time it reaches the bottom. The sun sits at the bottom of the deepest valley there is, the deepest gravity well in the solar system, and anything falling toward it picks up tremendous speed on the way in. A craft dropping in from far away can be moving well over 100 kilometers every second as it whips around its closest approach, faster than anything we have ever launched. That closest point, skimming just above the sun, is the single best place in the solar system to light an engine. So the maneuver goes like this. A spacecraft leaves the Earth and, instead of trying to climb, lets itself fall inward toward the sun, gathering speed the whole way down for free, spending no fuel at all. Picture it in stages. The craft turns inward, not outward. The sun swells in its view, larger than any spacecraft has ever seen it. The heat shield begins to glow. And at the brightest, fastest, most dangerous instant, deep at the bottom of the dive, the engine fires, hard, for only a few minutes, because the geometry is so favorable that a few minutes is all it needs. Moving that fast, the short burn buys an enormous change in its path, far more than the same fuel could ever buy out among the planets. Aimed the right way, the spacecraft comes screaming back out of the dive on a brand new orbit. Tilted up out of the plane, climbing toward the poles of the sun, the fall becomes the launch pad. The art of it lies in spending almost nothing on the way down. The fall itself is free, so a well-built mission arrives at the bottom of the dive with its tanks still full, every drop saved for the one moment it matters. Burn fuel early, out where the craft is still slow and most of it is wasted. Hoard it for the high-speed instant at the bottom, and it does many times the work. The whole plan turns on holding everything back until the single instant that pays the most. And the savings are not small. The straight climb out of the plane, remember, costs something near 30 kilometers a second, more than any rocket can carry. The diving maneuver can do the same job for perhaps 3 or 4. A tenth of the price, paid at exactly the right heartbeat, simply by letting the sun's own gravity do the hardest part of the work. It turns a trip that no rocket can make into one an ordinary mission could afford. This is not a new idea. It was written down nearly a century ago, in 1929, by Hermann Oberth, one of the founders of rocket science, long before any rocket had ever reached space. He worked out on paper that an engine fired deep in a gravity well at high speed would reach far further than the same engine fired out in the calm. The principle has carried his name ever since, and it sat in the textbooks for decades as a lovely piece of theory. Only now, as we hunt for an affordable way above the sun, is it finally moving from the page toward a real mission. This is not the same as the slingshot we saw before. A gravity assist borrows speed from a passing planet, taking a sliver of energy from something else. This dive borrows nothing from anyone. The energy all comes from the craft's own engine. The sun's gravity simply arranges for that engine to fire at the perfect moment when the craft is moving fast enough to make every drop of fuel count. It is a slingshot built from your own fuel and the sun's gravity, with no planet needed at all. There is one detail that decides whether the whole plan lives or dies. To burn at the bottom of the dive, the spacecraft has to survive the bottom of the dive. Skimming that close to the sun means facing a wall of heat and light, fierce enough to destroy an unprotected machine in seconds. The answer is a heat shield, a thick screen carried out in front, soaking up the full blast of the sun while the spacecraft hides in its shadow, cool enough to keep working. Out at the face of that shield, the temperature can climb past 1,000 degrees, while just behind it, a hand's breadth away, the instruments sit close to the warmth of a comfortable room. It sounds like the most fragile part of the whole idea. It is the part we have already proven. In just the last few years, a probe was sent to dive nearer the sun than anything humanity has ever built, skimming only a few million kilometers above its surface. Down there, the sun's gravity flung it to around 690,000 kilometers an hour, making it by far the fastest object human beings have ever made. It flew straight through the sun's outer atmosphere, the corona, sampling the solar wind at the very place it is born, where no craft had ever been. And it came through, again and again, sheltered behind its shield, sending its measurements home after every pass. The terrifying part of the dive, the heat and the blinding speed, is no longer a guess. We have done it. What remains is to add the well-timed burn that turns a dive into a climb. What stays with me is how the cheapest road up runs straight down. Every instinct says to point the rocket where you want to go and push. The sun answers that the way to rise farthest is to fall first, fall fast, and spend your strength all at once at the very bottom. The engine matters far less than the moment you choose to fire it. And yet even a perfect dive is a single violent shove. A craft that falls, burns, and climbs out of the plane is still, in the end, flung onto an orbit, sweeping up and over and back down again, much like the ones before it. To truly settle above a pole and stay there, watching for years, you would want the opposite of a violent shove, something gentle, endless, and free. There is one more way up, and it carries no fuel whatsoever. It does not fight gravity, and it does not dive. It simply leans on the light. So could a spacecraft climb out of the plane on nothing but sunlight, and once it is up there, never have to come back down. The last way up is the strangest of all, because it runs on something that hardly seems able to push anything at all. It runs on sunlight. Not the sun's wind of particles, but the actual light, the same light falling on your window right now. Light, it turns out, can push, and a spacecraft can ride that push the way a boat rides the wind. It is hard to believe at first, because light has no weight. A beam of sunlight weighs nothing and carries no mass at all. But it carries something else. Momentum. A kind of motion packed into every particle of light, every photon. When a photon strikes a surface and bounces off, it gives that surface a tiny shove, the same way a thrown ball shoves whatever it bounces off. And because a mirror sends light straight back the way it came, a shiny surface gets pushed twice as hard as a dark one, once as the light arrives, and again as it leaves. So a bright, mirror-like sheet, held up to the sun, feels a real and steady push. That light could push at all was first predicted from the laws of electricity and magnetism back in the 1800s, and measured in a laboratory around the year 1900, long before anyone dreamed of sailing a ship on it. How big is that push? Almost nothing. Sunlight falling on a sail is so gentle that a sail the size of a football field feels a push no greater than the weight of a small coin resting in your palm. You could stand a sail out in full sunlight and never see it so much as twitch. So why would anyone build a spacecraft around a force that faint? Because of two things the faint push has that no rocket does. It never stops, and it costs nothing. A rocket fires for minutes and is finished. A sail is pushed every single second, of every hour, of every day, for as long as the sun shines on it. And a tiny push that never, ever stops will, given enough time, outrun a single hard shove. The Oort dive is a gambler's move, everything spent in one violent instant at the bottom of a fall. The sail is its patient opposite. It spends nothing, and simply leans into the light, year after year, gathering speed so slowly you could never watch it happen, until the total change in its motion grows enormous. And nature has been flying solar sails for as long as there have been comets. A comet's tail does not trail behind it like smoke off a train. It points away from the sun, no matter which way the comet is traveling, because sunlight is physically blowing the comet's dust outward. Those great comets you may once have watched hang in the night were, in part, enormous ragged sails shoved across the sky by light. The sail itself is a marvel of thinness. To catch a useful amount of that gentle push, it has to be huge, thousands of square meters, the size of several sports fields stitched together. And it has to be almost impossibly light, a shimmering film just a few millionths of a meter thick, far thinner than a human hair, thinner even than the plastic wrap in your kitchen. Folded down small for launch, it unfurls in space along slender booms, spreading out into a vast, silver, mirror-bright sheet, hanging weightless in the sunlight. And like any sail, you can steer it. A sailing ship does not only run straight downwind. By angling its sail, it can cut across the wind and even work its way upwind. A solar sail does the same with light. Tilt the sail one way, and the sunlight's push adds energy to the orbit, widening it. Tilt it the other, and the push bleeds energy away, drawing the orbit inward. And tilt it just so, and the push leans on the whole orbit, tipping it up a little more on every loop, out of the flat plane and toward the poles. The wind it tacks against is not air, and it is not the solar wind, it is the light itself. The closer a sail drifts toward the sun, the brighter the sunlight falling on it, and the harder the push. So a sail spiraling inward does not merely survive the approach. It grows stronger as it goes, the light thickening around it, the gentle force swelling the nearer it comes. The sun rewards the sail for drawing close. And the great prize of the sail is the one thing the dive could never give. A sail never runs out of fuel. As long as the sun is shining, it has thrust, so a sail-driven craft does not have to settle for one pass and a long fall back. It could climb out of the plane, rise above a pole, and then simply stay there, holding its place, maneuvering as it likes, watching the pole turn beneath it for years on end. The thing no machine has ever done, hovering over the top of the sun and keeping watch, is precisely the thing a sail is built to do. The price, of course, is time. That faint push works slowly, and a sail bound for the sun's poles might spend years patiently spiraling its way up, where a dive would arrive in a fraction of that. A sail mission is a long, quiet investment. It asks for patience in place of fuel, and trades years of waiting for a freedom of movement no fuel tank could ever buy. This is not only a dream on paper, either. Small experimental spacecraft have already unfurled real sails in space and felt the push of sunlight move them, some even nudging their own orbits higher on nothing but light. The principle is proven. The films work, the booms deploy, the gentle force is real and measurable. What has never been built is a sail at the grand scale, thousands of square meters across, aimed at the poles of the sun. Mission designers have drawn up those grander sails for decades. Plans for a sail that spirals slowly inward, raising its tilt loop by loop until it rides high over a pole, have been worked out in careful detail more than once. The most promising of them braid together the two ideas we have seen: a sail to do the slow, cheap work of getting into position near the sun, and then an Oberth dive and burn to fling the craft sharply up out of the plane. The patient climb of the sail, married to the violent shove of the dive, each one covering for what the other lacks. Every piece has been designed, none of it has been flown. The mission waits, as so much does, on money and will, rather than on any law of physics. And the force at the heart of all of it is touching you right now. The sunlight resting on your skin, the warmth on the back of your hand near a window, is not only heat, it is a push, light pressing gently on you, far too faint to feel, and entirely real. You are being pushed by the sun this very moment, by a force too small for your body to ever notice. Spread that same push across a mirror the size of a stadium, and let it work without rest for years, and it becomes a way to sail above a star. Set the three ways up side by side, and the sail is the gentlest by far. No fuel, no fire, no violence, only a weightless beam of light, and enough time to let it do its work. The most powerful thing in our sky, given the lightest possible touch, quietly becomes a road. So we are not, in the end, trapped. Between the dive and the sail, there are real ways to climb above the sun and finally look down. The poles of the sun are one reason to make that climb. They are not the largest. There is something far bigger waiting up there to be seen, something we have circled all night without ever quite facing, and it is not the sun at all, it is us. Our own home, the bubble we live inside, has never once been seen from the outside. We have mapped every planet and crossed the edge of our own bubble with 2 drifting probes, and we still do not know what the thing we live in actually looks like. So what shape is our home, really, and why has no one ever seen it? we do not know the shape of our own home. Not the Earth. The Earth we have mapped down to the last coastline. The home that is larger than all of it. The great bubble of the sun's wind, the heliosphere, the outermost wall of everything we belong to. We have lived our entire existence inside it, and we have never once seen its shape. Hold that up against everything else we have done. We have photographed the surface of Pluto, billions of miles away. We have mapped the moons of Jupiter, the rings of Saturn, the canyons of Mars. We have charted galaxies whose light left them before the Earth was born. And the one outline we have never drawn is the outline of the thing we are sitting inside at this very moment. It is like living your whole life in a house, knowing every room, every creak of every floorboard, and never once stepping out the front door to see what the house looks like from the street. We know our home from the inside, in perfect detail. From the outside, we have never seen it at all. For most of the last century, we believed we knew the shape anyway. The picture was a comet. The sun drifts through the thin gas between the stars, plowing forward, and that motion was thought to mold the bubble the way moving through anything molds it. A rounded nose pushed up at the front, where the sun presses into the oncoming gas, and a long, streaming tail drawn out behind, trailing away into the dark. It was a reasonable guess. We see bubbles shaped like that around other stars, glowing where their winds push into the gas around them. So we drew our own home as a great cosmic comet, head and tail, and set it down in the textbooks. The trouble is how little of it we have actually touched. Only 2 spacecraft have ever reached the edge of the bubble and crossed it, the 2 Voyagers. And both of them crossed near the nose, on the front side, and both roughly within the flat plane of the planets. 2 crossings, in nearly the same direction, out of a boundary that wraps around us in every direction there is. It is the old story of feeling an elephant in the dark. One hand on the trunk, another beside it on the same trunk, and from that you try to picture the whole animal. We have touched our home's wall in one small place, twice, and from those 2 touches we have been trying to imagine the entire thing. And what those 2 crossings found was already stranger than the simple comet picture had promised. The boundary was sharper than expected, and the magnetic field just beyond it lay at an odd, tilted angle, a hint that the gas pressing in from outside was shaping the wall in ways the old model never allowed for. Then, recently, the whole shape came into doubt. In 2020, a team led by the physicist Merav Ofer, studying how the bubble meets the magnetic field threaded through the gas between the stars, arrived at a startlingly different answer. The heliosphere, in their work, is not a comet at all. It has no long tail. It looks more like a deflated croissant, 2 rounded lobes curving back from the nose, pinched together at the waist, with no streaming tail behind it. Think of the sun's magnetic field lines as rubber bands wrapped around the bubble. Stretched into a long tail, they would have to keep stretching forever. Instead, they snap the bubble shut at the back, like a balloon tied off at its neck. A comet with a tail, or a compact, curled croissant with none. 2 completely different shapes for the same home, and from inside, we still cannot say which one is real. So people found a way to look without going there. The trick is beautiful, and it uses no light at all. It uses particles. Out at the boundary, charged particles of the solar wind keep colliding with neutral atoms drifting in from interstellar space. Now and then, in one of those collisions, an electron jumps across, and a fast-charged particle becomes a fast neutral atom. A neutral atom feels no magnetic field, so it stops curving and simply flies in a straight line, and some of them come flying back into the inner solar system, all the way to instruments waiting near the Earth. Each one arrives carrying the memory of where it was born, out on the boundary. By catching these returning atoms from every direction, noting which way they came and how fast, we can slowly build a map of the boundary, the way a doctor builds a picture of the inside of a body from signals passing through it, without ever cutting it open. And the first time we made that map, the boundary handed us a mystery. Stretched across the sky was a long, bright ribbon, an arc of far more of these returning atoms than anywhere else, a feature no one had predicted. Years later, its origin is still argued over. It seems tied to the direction of the magnetic field in the gas just beyond our bubble, the field pressing in on our home from the galaxy outside. Whatever it is, that ribbon told us plainly that the edge of our home has structure we never expected, written in a language we are only beginning to read. A new probe is being readied now to map that boundary far more sharply, catching those returning atoms in much finer detail to settle which shape is right. It is a powerful tool, but notice what it still is. It maps the boundary by inference, from the inside, by the particles that drift back to us. To truly see the shape of our home, to look at it the way we look down at the Earth from orbit, someone would have to climb high above the plane, out past the disk, turn around, and look back. And that is the one thing we have never done. The probe that could draw the portrait of our home from outside has never been built. It is stranger still, because the bubble does not even hold a single fixed shape. It breathes. As the sun grows stormy and then quiets across its long cycle, the wind pushes harder and then softer, and the whole boundary swells outward and draws back in. And the sun is drifting through patches of interstellar gas that are not all the same, some thicker, some thinner, so the bubble is squeezed and released as it travels. Whatever portrait we finally draw will be of a living thing, a wall that flexes and shifts, never quite the same twice. This is a strange thing to have to say out loud, this late in our exploring. We have drawn careful maps of worlds we will likely never visit, and we have never once drawn the outline of the room we have spent our whole existence inside. The wall around you tonight, the bubble that turns aside most of the harsh radiation of the galaxy and keeps the Earth gentle enough for you to be lying here at all, is a wall whose shape no one has ever seen. We know that it is there. We do not know what it looks like. And so the missing view becomes the quiet center of the whole night. Every reason to climb above the sun gathers right here, not only to see the poles, but to turn around, at last, and look back at our own home spread out below. Suppose a craft finally did make that climb, the sail and the dive carrying it up out of the plane, until it floated high above everything, and it turned its gaze downward. What would it see, looking back at the only home we have ever had? The first thing the craft would do, having climbed all that way, is turn its gaze downward. And it would see something no human being has ever seen, the entire solar system, all at once, as the flat thing it truly is. From inside the plane, we have only ever pieced the layout together. We know where the planets are by tracking them, calculating, inferring, the way you might map a city by walking its streets, one at a time, never once seeing it whole. From high above the plane, all of that collapses into a single glance. The disk, seen at last as a disk, the sun blazing at the center, and the planets strung around it in a wide, flat ring, each one a bright point easing along its own circle. The faint sheet of dust we met earlier, the stuff that makes the zodiacal glow, spread out below like a vast, dim, luminous plate. Everything we have ever known, laid flat in a single frame, lit from the middle. Look closer at that ring, and the structure leaps out. The asteroid belt between Mars and Jupiter would show not as the crowded rubble field of the movies, but as what it actually is, a thin, sparse band with vast empty gaps between its rocks. All the asteroids together would not add up to even the mass of our moon, scattered so thinly that you could fly straight through the belt and never come near a single one. And the gaps in it are not random. Jupiter's gravity, tugging again and again at the same steady rhythm, has swept certain rings of the belt nearly clean, leaving dark lanes carved into the band. Out along Jupiter's own orbit, two great swarms of asteroids would sit, one running ahead of the giant and one trailing behind, herded into those two spots and held there by the balance of gravity. From above, that whole sculpted pattern, the gaps, the swarms, the bands of dust, would stand out in a single look, a thing we have only ever rebuilt piece by piece from inside. The comets would show their hand, too. The faint trails of dust they leave along their paths, the thin rings shed by the bodies of the inner system, all of it would sort itself out against the dark, each source of dust finally told apart from the others. The whole slow machinery of the plane, grinding and shedding and drifting, would be visible as one connected thing. The planets themselves would be points of light threading slowly along their tracks. And the small tilts we talked about near the start, Mercury riding a little high, Pluto swinging well above the ring and below it, would no longer be numbers in a table. They would be plainly visible. This world sitting a touch above the plane, that one dipping beneath it, the real, slightly imperfect flatness of our home, shown all at once. The thing we have only ever described would finally just be there, to look at. We have come close to this only once, and only barely. Long ago, on its way out of the solar system, one of the Voyager spacecraft turned its camera around and took a set of photographs looking back. In one of them, the Earth showed up as a single pale dot, smaller than a bright spark, lost in the glare, caught inside a thin beam of scattered sunlight. It is one of the most famous images ever made. But it was taken from far out, and from nearly within the plane, the planets strung along faint arcs, grainy specks in the dark. It was a portrait caught nearly edge-on, in passing, from inside the room. The true overhead portrait, the whole disk seen face-on as a single structured object, has still never been made. We have a snapshot of home from the doorway. We have never once stepped back to take the family photograph. The shape of our bubble. A craft riding high above the plane could measure the boundary of the heliosphere from angles no Voyager ever reached, at the top, off to the sides, far from the single patch where the two probes crossed. If it climbed far enough and lasted long enough, it might even cross that boundary itself, from above or below, the first crossing ever made outside the flat plane. From those measurements, the comet and the croissant would stop being two rival guesses. One of them would simply be shown to be true. And from up there, it could watch the bubble breathe across the years, swelling and shrinking with the sun's long cycle, the great ballerina skirt of the current sheet rippling out beneath it. The outline of our home, argued over for years, drawn only from clues, would at last be drawn from sight. The difference between a map sketched from footprints and faint echoes and a photograph taken in plain daylight. Every other home we know, we picture from the outside without even thinking, a house, a town, a country on a globe. Our largest home, the solar system itself, we have only ever known from within. The climb would hand us, for the very first time, the view from outside our own walls. And somewhere in that flat ring of light, you could find a single faint point and know it for what it was. The Earth, The whole of it. Every ocean, every city, every person who has ever lived or ever will, the entire human story, resting on one small speck, threading its way around the sun, in a picture finally taken from far enough away to hold all of it at once. You are on that speck right now, in the dark, listening. Of all the images astronomy has ever gathered, from the surfaces of distant moons to the glow of the newborn universe, the one we are still missing is the simplest one of all. A clear photograph of the place we are standing. We have pointed our cameras at nearly everything except the thing they are sitting inside. The last portrait left to take is the portrait of home. But looking down is only half of what that vantage would offer. Turn the same craft the other way, away from the sun, away from the dusty plain, and point it out into the dark. Up there, above the haze that has fogged every telescope we have ever built, the rest of the universe would be waiting, clearer than we have ever managed to see it from anywhere inside our home. So what would the universe itself look like? Seen from above all of our dust. Now turn the craft the other way and point it out into the dark. The first thing you would notice is the dark itself. The sky out there would be deeper, blacker, emptier than any sky you could ever reach from down inside the solar system. Remember the dust. That faint sheet of grain spread through the plain, the stuff that makes the zodiacal glow on a clear night. From inside, it is always there, in every direction along the plain, a soft, scattered haze of sunlight that never fully fades. Even on the darkest, clearest night the earth can offer, that glow sets a floor. There is a faintness past which you simply cannot see, because the dust of our own home is always glowing in the way. Climb above the plain, though, and that whole glowing sheet drops away beneath you. The haze falls behind, and the sky overhead opens into a darkness cleaner than anything possible from within the disk. You already know this difference in your bones. Stand in a city at night and look up, and you see a handful of stars swimming in a dull orange wash. Drive hours out into the desert, far from every light, and look up at the same sky, and suddenly it is crowded, thousands of stars, the soft band of the Milky Way, depth upon depth of them. Same sky. The only thing that changed was the glow you were looking through. A telescope above the plain would be sitting at the darkest site there is, the desert of the entire solar system, with the nearest glow finally behind it. And in that darkness, things we strain at today would come within reach. Begin with the search for life. Out among the stars are countless other worlds, and on some of them there may be faint chemical traces of living things, written into the light of their atmospheres. What gives a living world away is a particular mix in its air, gases that should not sit together unless something keeps remaking them, like oxygen and methane found side by side. But that light is unimaginably faint, a whisper beside the roar of the star it circles, and one of the things drowning the whisper, here at home, is our own dust, scattering stray sunlight into every telescope we point outward. A telescope lifted above the plain would look out through a far cleaner window, the haze gone, the background dark, and the faintest signals from distant living worlds would finally have a chance to come through. Then there is the oldest light of all. Filling the whole sky, in every direction, is a faint, even glow left over from the birth of the universe. The light set free a few 100,000 years after everything began, when the first atoms formed. It carries the imprint of how the cosmos started, written in tiny ripples of temperature across the sky. Those ripples are the seeds that everything grew from, the faint unevenness that later became galaxies and clusters and us. Reading them precisely is how we measure the age of the universe and what it is made of, and the single hardest part of that work is subtracting every nearer source of glow standing in front of it. From above the plane, the glow of our own dust thins away, and the most ancient light in existence could be measured more sharply than ever, the first moments of the universe brought into clearer focus. The trouble is worst in infrared light, the warm part of the glow that is most useful both for finding planets and for studying that early universe. In infrared, our own dust is one of the brightest things in the entire sky, a wall of warmth we cannot get behind from in here. To rise above it is to uncover a whole band of the universe we can barely use from where we stand. Even ordinary stars would give up more of their secrets. So much of astronomy is the hunt for small changes, a star that flickers, a distant beacon that pulses, a faint cold world that slowly brightens and fades. Every one of those small signals is easier to catch against a darker background where nothing local is washing it out. A cleaner sky would sharpen nearly every kind of looking we do. The direction with the least in it, straight up out of the plane, is the most valuable direction there is to look. The dust that draws our home, the lovely cone of light you might catch on a dark night, the disk that holds the earth and the sun and all the warmth, is the very same dust that hides the rest of the universe from us. Our home and our blindfold are one and the same flat sheet. To see the cosmos most clearly, we would have to rise above the very thing that shelters us. You have felt the smaller version of this every time you left the city lights behind. The sky did not change. You simply stepped out of the glow and saw what had been there all along. A craft above the plane would be doing the same thing, on the largest scale there is, stepping out of the glow of our entire home and seeing the universe as it always was, waiting just past our own light. There is a clean symmetry to the whole idea. Looking down, the climb hands us the first true portrait of home. Looking up, from the very same spot, it hands us the clearest view of everything that is not home. One vantage, two gifts, pointed in exactly opposite directions, and we have never once stood there to receive either. And as that clean window swung toward one particular direction, the view would open further still. Because the space immediately around our sun is not ordinary space. We happen to be drifting through a strange, unusually empty pocket of the galaxy, a great low cavity scooped out of the gas between the stars, and along certain lines of sight, it lets us see farther and clearer than almost anywhere else. Something hollowed that pocket out, long before there were any people to drift through it. So why is the space around us so empty? And what could possibly have cleared it? The emptiness around us is not natural calm. It is the aftermath of violence. Our sun is drifting, right now, through the middle of an enormous hollow blown into the gas of the galaxy, a great cavity where the thin material between the stars has been swept nearly clean. Astronomers call it the local bubble, and we are sitting close to the heart of it. It is staggeringly large. By recent measurements, the bubble stretches something close to 1,000 light-years from one side to the other. Light itself, the fastest thing there is, would need a full 1,000 years just to cross from one wall of it to the far one. And throughout that whole vast volume, the gas is far thinner than the galaxy's average, a near emptiness scooped out of the ordinary dustiness of space. The sun, with all its planets, is simply passing through the cleared-out middle of it. So what scooped out a hollow 1,000 light-years wide? Not one event, a long string of them. Over roughly the last 14 million years, something like 15 massive stars clustered in this region, reached the ends of their short, brilliant lives and exploded, one after another, as supernovae. Those exploding stars were not loners. They belonged to great drifting herds of young, heavy stars, born together and traveling together, and we can still pick out their surviving siblings in the sky nearby. The ones that died were simply the heaviest, the kind that burn fastest and detonate first. Each explosion flung out a shock wave that shoved the surrounding gas outward, the way a blast clears smoke out of a room, piling it up and pushing it back. Explosion after explosion, across millions of years, those shock waves swept this whole region nearly empty, carving the cavity we now drift through. The quiet, clean space around us is the scar left by a slow bombardment of dying stars. And the swept gas did not simply vanish, it piled up at the edges. All that material, shoved outward by the blasts, gathered into a dense shell around the rim of the bubble, like snow heaped at the edges of a cleared lot. And on that shell, something remarkable is happening. The piled-up gas grew dense enough to collapse and form new stars. Nearly all the young stars and star-forming clouds anywhere near us turn out to sit on the surface of this bubble, strung around its rim. The very explosions that emptied the inside swept up the walls, and on those walls a fresh generation of stars is now being born. The bubble is a blast crater that became a nursery. Now, how could anyone possibly know all this happened, millions of years before there was anyone to see it? Part of the answer is buried in the floor of the sea. Down in the slow mud of the deep ocean, laid down over ages, there is a particular kind of iron, a radioactive form called iron-60. And iron-60 almost never forms on Earth. It is made, above all, in the hearts of exploding stars. Finding it in the seabed is like finding ash from a fire in a house that has never had one. It could only have been carried in from outside. What makes it so powerful is that iron-60 is both a clock and a fingerprint. It is radioactive, so it slowly decays. After about 2.5 million years, half of whatever was there is gone. So any iron-60 still sitting in the ground today cannot be ancient. It must have arrived recently, in cosmic terms, long after the Earth itself formed, or it would have decayed away to nothing by now. And because it is forged in supernovae, its mere presence points back to a nearby exploding star as its source. Read the layers of seabed mud, and the iron-60 shows up in particular bands, telling us that the debris of nearby supernovae rained down onto the Earth around 2 to 3 million years ago, and again further back. The mud holds a dated record of the deaths of nearby stars. The timing of that strongest pulse has drawn a good deal of attention. It lands close to a stretch, around 2 to 3 million years ago, when the Earth's climate was cooling and shifting. Whether a nearby supernova could have nudged that climate, perhaps by changing the rain of cosmic rays reaching us, is still an open and uncertain question. The dust is real, and it is dated. What it did to the Earth, if anything at all, we do not yet know. And the ash is, in a sense, still falling. Traces of this same supernova iron have turned up not only in ancient seabed layers, but in fresh Antarctic snow, in soil brought back from the moon, and even riding among the cosmic rays that stream through the solar system. The fallout from those long-ago explosions is still drifting down onto our world, even now. The sun crossed into this bubble only about 5 million years ago, and it has been moving through the aftermath ever since, gathering a fine, faint snowfall of stellar ash the whole way. Step back and the layers nest one inside another. The sun's own wind blows the heliosphere, that bubble whose shape we tried to find earlier. The heliosphere sits inside a small, slightly denser clump of gas the sun is passing through right now. And that clump sits inside the great local bubble, the 1,000-light-year cavity carved by the supernovae. A bubble, within a cloud, within a far larger bubble, each one folded inside the next. And the near emptiness of that outermost bubble is the very reason our view outward, that clean window we just imagined, is as clear as it is. We are looking out through a hole that exploding stars blew in the fog for us. And this reaches all the way down to the ground beneath you, and into your own body. The iron in the rocks under your feet, the iron in the blood moving through you at this moment, was forged inside stars and scattered when they died. That much is true of everyone, everywhere. But this is more particular than that. Atoms from specific nearby stars, ones that exploded while our own ancestors were beginning to walk upright, have settled onto this planet, into its seas and its soil, within the span of our own long family story. The dust of those deaths is not a figure of speech. It is measured, layer by layer, in the mud at the bottom of the sea. It is a strange thought that the shelter and the violence are one and the same. The clean, quiet, empty space that lets us see the universe so clearly, the calm pocket our sun drifts through, was made by a string of the most violent events the galaxy can produce. We live inside the long, settling silence after an explosion, reading the story of it in iron and in snow. And the bubble, for all its size, is not the end of the nesting. Zoom out one final time, far above not just the plane of the planets but the whole of it, and the bubble itself is only a small pocket inside something vastly greater. The flat, turning disk of the Milky Way, countless stars wide, tilted at a steep angle to our own little plane. From high above the sun, even the galaxy would hang at an unfamiliar slant, rearranged. So how does the rest of the galaxy look from above our own star, and where, in all of that turning, are we actually going? The same simple recipe that flattened our solar system, spinning plus gravity, built something almost unimaginably larger, the galaxy itself. The Milky Way is a disk too, a flat, slowly turning wheel of countless stars, with a bright bulge at its center and great spiral arms winding outward. Everything we have spoken of tonight, the sun, the planets, the bubbles, and the dust, all of it sits inside that one enormous disk, far out toward the edge, in a quiet minor arm. And the two disks do not line up. Our little plane of planets is not laid flat within the galaxy's great plane. It is tilted, steeply, by around 60 degrees. Picture a small coin set down at a steep slant on the face of a vast, slowly spinning record. The coin is our solar system. The record is the galaxy. The two are turning in completely different planes, our small one tipped over inside the enormous one. This is why the sky would look so strange from above the sun. From the Earth, the Milky Way appears as a soft band of light stretched across the night, the edge of the galaxy's disk seen from within it. But climb high above the sun's pole and turn to look, and that familiar band would no longer lie where it does for us. It would tilt sharply, swung around to a steep new angle, the glowing center of the galaxy resting in a direction we have never seen it from. The same stars, the same Milky Way, hung in an arrangement no human eye has ever had. And none of it is still. The sun is not parked in the galaxy. It is racing around the galactic center, carrying the whole solar system with it, at something like 230 kilometers every second. Even at that staggering speed, the galaxy is so vast that a single full lap takes around 230 million years. One trip around counts as a kind of year, a galactic year. And in the sun's whole long life, it has completed only about 20 of them. To feel how long one lap is, consider this. A single trip around the galaxy takes longer than there have been flowers on the Earth. The last time the sun stood where it stands now in its orbit, no flower had ever bloomed. How could we ever know all this? The speed, the lap, the weaving. By patiently tracking the motions of more than 1 billion stars at once, slowly mapping the whole great wheel as it turns. And that mapping has held surprises. The disk is not perfectly flat. It is warped along its edges and faintly rippling, as if something large passed through it long ago and set it gently ringing like the surface of a pond. The path is not a flat circle either. As it orbits, the sun bobs gently up and down through the crowded central layer of the galaxy, rising above that dense midplane and then sinking back down through it, over and over, like a horse on a carousel that also rides slowly up and down. We are weaving as we circle, threading above and below the galaxy's own plane on a long, slow rhythm of tens of millions of years. Right now we sit a little above that midplane, drifting upward. And we are headed somewhere in particular. Set against the nearby stars, the sun is drifting toward one specific patch of sky in the direction of the constellation Hercules. That is the way we are going, the bow of our ship, the point the whole solar system is quietly sailing toward through the sea of nearby stars. We are not simply adrift, we are aimed. Now look beyond the flat disk of the galaxy entirely, far above it and far below. The bright spiral disk is not the whole of the Milky Way. Wrapped around it is a vast, dim, roughly spherical region called the halo. Out there, above and below the crowded disk, drift the oldest stars in the galaxy, ancient globular clusters of them formed when the universe itself was young, long before the disk ever settled into its spiral. And we know there is far more out there than those old stars, because the stars at the galaxy's edge swing around far too fast for the gravity of all the visible matter to hold them. Something heavier and invisible must be gripping them. Most of the galaxy, it turns out, is made of a kind of matter we cannot see at all, gathered in that great halo above and below the disk. The galaxy, like the solar system, has its flat, busy plane and its quiet, mysterious above and below. Relative to the plane of the planets, there is an above and a below. Relative to the plane of the galaxy, there is a different above and below. Every scale has its disk, its perpendicular, its quiet shell wrapped around the busy middle. Up was never one single direction. It was always a choice of which flatness you happened to be standing on. Stack it all together, and the layers run staggeringly deep. A planet, riding inside the heliosphere, the bubble of the sun's wind. The heliosphere inside a small interstellar cloud. That cloud inside the great local bubble carved by supernovae. The bubble. Inside a minor spiral arm. The arm inside the vast flat disk of the Milky Way. The disk wrapped in its spherical halo of old stars and dark matter. And the whole galaxy, in turn, just one member of a small cluster of galaxies, adrift in a far larger sea. Shell within shell within shell, each one turning, each with its own quiet history, each folded inside the next. And you are riding every single one of those motions at once, right now, lying perfectly still. turning with the Earth, sweeping around the Sun, bobbing through the galaxy, carried toward Hercules, drifting with the whole cluster through the universe. A stack of motion so vast and so smooth that you feel none of it, just as you never felt the 30 kilometers a second from the very start of the night. The Sun has carried you, and everything you have ever known, around this galaxy, some 20 times, and not once has anyone felt the wind of it. And all of it, every shell and every orbit, would go on turning exactly as it does, whether or not a single person ever climbed up to look. The Sun would still spin, the poles would still flip, the bubble would still hold its unseen shape, the galaxy would still wheel, with us or without us. The missing photograph, the unseen shape of home, the poles we have only just glimpsed. None of the universe out there is waiting on us to come and see it. So if the cosmos does not need the picture at all, then who, exactly, is the missing view for? The answer is quietly simple. The view is not for the universe, it is for us. The Sun does not need to be photographed from above. The galaxy does not need a witness to keep turning. The missing picture would change nothing at all out there. It would only change what we know, and what we have seen, down here. And the most surprising thing about that picture is this: we could take it. Not someday, in principle, after some breakthrough that has not happened yet. The mission to climb above the Sun and look back is not waiting on any new physics. Every hard piece of it has already been done, somewhere on its own. Walk back through the night and count them up. Gravity assists, the planetary slingshots, are routine. We have flown them for 60 years. The Oort dive, the fall toward the Sun, and the burst of an engine at the bottom, rests on a principle understood for nearly a century, and we have already sent a probe straight into that furnace, at that exact speed, behind a heat shield that held again and again, and brought it home. We have unfurled real sails in orbit and watched sunlight nudge them higher. We have flown gentle electric engines out to asteroids and comets, pushing softly for years and arriving exactly where we aimed. Every separate trick the climb would need has already been demonstrated. None of it is science fiction. And the missions themselves have been designed again and again. For decades, careful people have drawn up the plans, a great sail that spirals slowly inward and tips its orbit higher loop by loop until it rides above a pole, a craft that dives to the Sun and burns at the bottom to fling itself out of the plane. A patient observatory, running on steady electric thrust, that could climb above the Sun and simply hold there, watching a pole turn beneath it for years. These are not sketches on a napkin. They have been modeled in detail, costed, refined, written up, studied, shelved, and revived, more than once, across more than one space agency and more than one generation of engineers. The blueprints exist. The vehicle has simply never been built. The most promising plan braids the gentle and the violent together. A sail to do the slow, free work of carrying the craft in close to the Sun, then a single dive and burn to throw it up out of the plane, and the sail once more to settle it above a pole and hold it there, each piece quietly covering for what the others lack. The patience of the sail, the punch of the dive, the steadiness of the electric engine, all in one ship. So if the physics is ready and the designs are drawn, what is the climb actually waiting on? Not knowledge. Money and priority and timing and the slow human business of deciding that this view, out of all the views we could buy, is worth the cost. There are only ever so many missions a generation can fly, and each one competes with all the others, the landers and the telescopes and the trips to other planets. The climb above the sun has been proposed and admired and passed over more than once, always for a later year that has not yet arrived. There is a nearer step already on the way. A new probe is being readied even now to map the edge of our bubble far more sharply than before, from the inside, by the faint atoms that drift back to us from the boundary. It will sharpen the picture and narrow the guesses about our home's true shape. But it is still a view from within the disk, an inference, a map drawn from clues. The true outside view, the climb above the plane to turn and look back, is the one still waiting, undecided, unbuilt. And there is a particular kind of patience buried in all of this. A mission like this takes decades, from the first sketch to the final picture. The person who first draws the trajectory may hand it on to others, and they to others again, before any craft ever leaves the ground. It is the slow, generational work of people quietly building toward a photograph that some of them will not live to see developed. Whole careers spent reaching toward a single unfamiliar view of home. So who is the missing view for? It is for us, for the simple, deep want to finally see the place we live from the outside, the way we have seen everything else. Think of how easily you can picture a neighbor's house from the street, or your own town from above, or the whole round earth hanging in space. Our largest home is the one place we have never once been able to picture that way. The climb would fill in the single blank square left on the map of where we live. To look at our own star's hidden face, and our own bubble's true shape, and our own flat home seen whole, not because the universe requires it, but because we are the kind of creature that wants to look. The picture is not for the sun, it is for the ones who have spent their whole lives inside its light, quietly wondering what it all looks like from just a little further out. And the gentlest part of the whole thing is this: none of it asks anything of you tonight. The climb can wait, the photograph can wait, the blueprints sit patiently on their shelf, the trajectories calculated, the ships that would fly them not yet built, and the waiting harms nothing at all. The sun has turned at the center of its flat disk for 4.5 billion years without that picture, and it will turn for billions more, with us or without us, watched or unwatched. The missing view is not a loss hanging over us. It is a quiet promise, set down for some future night, for hands that have not yet been born. The poles will keep flipping. The bubble will keep holding whatever shape it holds. The galaxy will keep wheeling, slow and enormous, carrying you along with it through the dark. None of it needs your attention now. None of it is asking you to stay awake. So, perhaps the only thing left to do tonight is the thing we have rarely managed as a species: to simply rest here, inside the home we have not yet seen from the outside. Not the question of what is above the sun or below it, just this: to lie still and let yourself be carried. So let yourself be carried. Not as an idea, but as the plain fact that it is. Right now, lying where you are being carried by every motion we have followed tonight, all at once, all of them perfectly smooth, all of them holding you without asking a single thing in return. Start with what you are made of. That cold, slow, turning cloud from the very beginning of the night, the one that flattened into a disk and lit a star at its center, did not only build the sun and the planets, it built you. The same gathered dust and gas became the rock beneath your house, the water in your glass, the calcium in your bones, the breath moving in and out of you at this very moment. You are not someone watching the solar system from the outside. You are a piece of it that woke up, made of its leftovers, lying inside it in the dark. And the same simple law that flattened that cloud, that a turning thing pulled inward must turn faster, is not a distant rule kept far away in space. It is in you, in the spin of a skater pulling her arms in, and faintly in your own body each time you roll over in the dark and quietly find your balance. The physics that shape the disk is the physics of your smallest movements. Feel the warmth, too, if any of the day's sun is still in the room. That warmth came from the same star whose hidden face we only just learned to see, the one that kept its poles turned away from us for the whole of human history. The light that crossed all that distance to reach your skin does more than warm you. It presses on you, ever so faintly, the same gentle push that could one day sail a ship above that very star. The sun you have never seen the top of has been touching you, quietly, every single day that you have been alive. And you are sheltered, right now, by the very thing whose shape no one has ever seen. The great bubble of the sun's wind, the one we could not draw the outline of, is wrapped around you at this moment, turning aside most of the harsh radiation of the galaxy, keeping this small world gentle enough for you to lie here and grow drowsy. You are resting inside a wall we have never once photographed, and it is doing its quiet work all the same. The iron carried in your blood, the iron that lets it carry air to every corner of you, was forged inside stars and scattered when they died. Some of those deaths happened nearby, and not so long ago, and their faint ash settled onto this very planet while our oldest ancestors were learning to stand. You are made, in part, of the same exploded stars that cleared the quiet pocket of space we drift through. Not as a turn of phrase, as a fact you could measure in the mud at the bottom of the sea. And beneath all of it, you are moving. 30 kilometers every second around the sun, more than 200 around the heart of the galaxy, bobbing slowly up and down through its great flat plane, drifting toward a far point in the constellation Hercules, carried with the whole galaxy through a wider dark still. You feel none of it. You never have. The motion is so steady and so shared by everything around you that it has always felt exactly like stillness. The sun has carried you, and everyone who ever came before you, some 20 times around this galaxy. This whole quiet night is less than a single blink in one of those long, slow laps. You do not have to do a single thing to be carried. It happens while you sleep and while you wake, and it has never once stopped. We spent tonight looking up and down out of the flat world we live in. We went searching for what waits in the one direction we almost never travel, and we found a great deal out there. The spherical shell of frozen comets, the bubble of the sun's breath, the hidden magnetic poles of our own star, the cleanest window onto the whole universe. But the strangest thing we found, looking out and up and away, was that every road led back here. The reason to climb above the sun was to turn around and finally see home. The cleanest view outward was, in the end, a view back toward ourselves. Perhaps, on some dark night, you even glimpsed it yourself. That faint cone of light leaning off the horizon, the disk of our home made briefly visible. You were looking straight down the length of the very thing you live inside. Up and down turned out to be just 2 more ways of pointing at the place we already are. None of what waits up there needs you to hold it tonight. The disk will keep its shape without your watching. The sun will keep turning at the center of it. The poles will flip on their slow clock. The bubble will hold its unseen form. The galaxy will wheel on, all of it carrying along exactly as it has for billions of years. whether you keep it in your mind or set it gently down. So you can set it down. Whatever you carried into this night, the thoughts, the lists, the small and large weights of the day, none of it is needed to keep any of this turning. The universe has the heavy lifting well in hand. There is nothing above the sun that asks anything of you. There is nothing below it that you need to reach tonight. The missing photograph can wait for someone else on some far morning. The trajectories can stay folded on their shelf. The poles can keep their slow turning, unwatched, exactly as they always have. And you can simply lie here, a small, warm piece of an enormous, quiet structure, carried by it, made of it, sheltered inside it, with nothing left to do but breathe and let the day go. Thank you for spending these hours here, in the dark, looking up. It is a quiet kind of company, to wonder about the same things together for a while, and I am grateful you chose to spend the time this way. Now let the sun rest where it always has, turning slowly at the center of its disk. Let the bubble hold its shape around you, whatever shape that turns out to be. Let the galaxy carry you onward, the way it always has, toward that far point you will never feel yourself nearing. And let the directions above and below the sun stay quiet, where they have waited all this time for some other night and some other looking. Let your breathing slow. Let yourself be carried. Good night.